Hope you all are fine in the middle of all this pandemic. The topic I have taken for presentation today is about self-propelled wheelchair design for hemiplegia patient. Now, this is a specific case that we took up as one of our students' father had this difficulty, and it was the wish of the student to do something for the father. So this project was taken up. The meaning of the terms self-propelled means if you have seen a regular wheelchair, you must have noticed it is the user who has to drive it, or maybe someone has to push or pull from behind, right? There are two ends available wherein you can hold and push or pull the chair, right? Now, self-propelled essentially means the force need not be exerted by us, as in by the human. It is machine driven. And hemiplegia basically means those patients who are partially paralyzed. Generally, whenever there is a paralysis attack due to whatsoever reason, it is one part of the body that loses movement, either the right hand side or the left hand side. And when we say it loses movement, it is reflected mostly on the entire side. So let's say if the right hand side is affected, it is the right arm, right leg which will lose the movement. The right eyeball will also not have much controlled movement. Even speech is affected, right? The reason we went for this kind of a project will be revealed as and how we continue with the session. Uh, I was the guide for the student, and the name of the student is Juhi Gupta. It is a final year UG project. We later on converted it into an IEEE paper publication also. The motivation behind it: a child made it for her father, the right side being paralyzed, controlling by the left hand for a person who is actually a right handed person, right, is definitely challenging. Continuous contact of the body with the seat and sides causes body sores. It's a friction, right? We have used Creo 3.0 version. Nowadays, Creo 4.0 is also available. But at the time when we were working on it, Creo 3.0 version was available and we used it. We tried to manufacture certain portions which were critical because they are lightweight, they are comfortable, and but of course the cost is high because the technology is still evolving, and maybe in due course of time the cost will hopefully go down. The reason we opted for this is, let us say, if I just go into a little bit of the uh, historical development behind it. We say handicap in general. It evolved from the word cap in hand because of the wars that used to happen in the 15th and 16th century for those disabled people who had to take to the streets so that they could manage to survive. And this was later replaced by the term disabled by the 20th century. And finally, as and how we started developing a human approach, the term has been replaced by a very dignified, differently abled person, right? And the motto behind is that we as technologists, we want to offer some support to those people who desire as well as deserve it. If you look at the World Report on Disability, the latest that we had available at the time of publication of our paper was in 2011. It turns out to be around 70 million people who suffer either from physical or mental disabilities. And not only that, there has been a critical increment from 2.13% in 2001 to 2.21% in 2011. That is a decade of difference. Uh, most of which is about mobility impairment, means the person is having a restricted movement, right? The majority of it is located in rural areas where the purchasing power is again highly limited. Of course, we know that there are automated chairs available in the market, but the concern is that some of the automated chairs have so many features which at times are not desirable. And the other concern being the features that are needed are actually not available, right? So these two factors actually inspired us to look into something where we could work upon. Okay, so we don't want to make the system unnecessarily complex by providing so many options. Remember, it was a one-to-one kind of setup where someone wanted to address the needs of a specific person and maybe later on extend it to the entire community, such that the wheelchair can be used in household and nearby locations, right? Not for all outdoor applications. So hemiplegia is more common than stated. What happens is that facial movements, we know, if you have learned a little bit about machine learning or artificial intelligence algorithms, they go by facial movements, right? So you can, lift your eyebrow, move your eyeballs, and those movements can be detected, and accordingly the wheelchair can move ahead, back, right or left, whatever way you want to control it. But remember, this facial movements, eyeball movements, mouth movement, even by speech, right? All these are restricted. In fact, the speech is quite incoherent in most of such patients. So, whatever regular automated wheelchairs are available in the market, they are basically based on the concept of feature extraction, right? And hence, we believe that that may be convenient for a specific section of the society, but probably it would not be able to offer the solution that we were looking for. And hence, a low cost, simple wheelchair is proposed that can be operated using any one arm, right? Remember, it's quite possible that the arm that is available for usage may not be the like it could be for a right-handed person, it could be the left arm that is available. That is what I want to convey, right? So the person will not be able to exert too much force because it is the other hand available, right? Either the patient or the caretaker, both can do it, both can have operation over it. The application, we made a mobile app also, and that could be downloaded into their smartphones, and with the help of that, free movement is possible. Apart from that, regular movement option is also open, right? It's not that you have to always use the app. If you want to go by physical method of pulling or pushing the wheelchair, that is also available. This is a broad level block diagram, uh, and many factors are not shown here, but they were actually implemented over there. I have tried to make this thing as concise as possible. Basically, we have used ultrasonic detectors, a set on the front hand side, another set on the back side. Now, what happens is that when we say that the wheelchair is machine driven, then the force, the speed is too large. In the sense, it's quite possible it may collide with the walls, or maybe some projections if they are there in the room, in the house itself, or maybe if the person is using in the periphery of the house, in the vicinity of the garden or the garage, right? So they tend to be very fast, and hence it is necessary to limit it at a specific distance. Now, this specific distance is programmable. So I may go for a distance of 30 centimeter. You may choose a distance of 60 centimeter. Either ways, it is going to work, because you just need to go to the program and change the value over there based upon your house calculations. You can always alter it, right? Of course, we are using Arduino. It's a very easily available device and very popularly used. Motors are used here for driving the wheels. Now remember, general wheels are very they are having high weight, right? So if the weight is large, then you need a different variety of motor drivers to drive a larger voltage motor, right? So uh, and this had to be battery operated, because we cannot afford to have wires dangling around, right? So if I just consider, if you remember the Excite car batteries that are there in your car, in your gearless machines like the Activa and all, right? The same kind of batteries can be utilized here also, right? So that, and it can be easily placed below the seat of the wheelchair. If you have noticed a wheelchair, below the seat there is a little space available, it can be fitted over there, right? So that it can supply power to the desired devices, right? So the motors part along with the drivers, of course. A Bluetooth module. Why do I need a Bluetooth module? Because Bluetooth is known to safely work within a range of 100 meters or so. That is, in general, we say within a house limit, within a house vicinity, it is going to perform to the best of its capacity. And anyhow, Bluetooth is available free of cost. You do not need to make additional installations, and it is very easy to operate also. Anyone and everyone can put on the Bluetooth um, icon on the phone and use it as a supporting help support system. So this is the broad block diagram. We can say there are certain things which I have not shown here. For example, when we considered the patient we had for our reference, we also implemented a small torch on the left arm side where the person could have access, right? The torch was meant to ensure that minimum light is available in case there is a light failure. And even if there is not a light failure, even in day to day life, by the time there is evening, from day to evening or day to night transition is happening, at that time the person has a provision to use a small source of light if needed, right? So there was a torch that was additionally placed, and there were many small things we made available for the person because it was dedicatedly made for some specific uh, person only. Okay. I am showing certain calculations here, but these calculations may vary from person to person. The we started with an assumption that the patient is weighing around 70 to 75 kgs, and the power requirement was 100 watt. Using a 100 rpm motor, we instead opted for 99 rpm motor. We found out what would be the radius of the wheel that will be needed if we want to drive it with the desired power. This is a small prototype. It is just tested with small motors. The same was extended to driver larger motors with corresponding drivers. This is the Android application. Uh, it is it's giving you the option to select your Bluetooth device, whatever you want to control it with, and with the help of this app, using MIT app, we could move the wheelchair left, right, forward, back, and stop. And this were the few basic motions that were needed. Not much was done in it, but we made sure that in case there is an obstacle coming in the path, that distance should be calculated and should be visible on the app. So if let us say the patient is slightly on the other side or maybe in some other room, and the phone is available, the phone of the caretaker is available with the person is in some other room or maybe in the same floor somewhere else, the person can still know if there is a chance of collision, right? So you can see on the top the obstacle distance is visible here, right? So whatever would be the distance in case of an obstacle turning up, it will definitely be visible here. The flow chart regarding the working of the smartphone application. So flowchart basically gives you an idea as to how these devices are connected and one after the other, right? The sequencing. So select Bluetooth device, display the distance from obstacle, and we had taken a distance of 40 centimeters as our reference. As I said, you can take any value. It may vary, and it is absolutely fine. It will be hopefully adjustable in the programming. If the distance is less than 40 centimeters, then you can work as per the buttons pressed in the Android application and it will be continuing to work. But in case it is less than that, right? So then in that case, it has to stop the motor immediately and make sure that the patient is safe at his position, whatever position he is at. Right. So this is the flow flow chart for explaining this small part that we had worked out. Basically, we are electronics and communication people, faculties and students from the electronics and communication department, and hence we generally opt for Proteus or Eagle for our circuit implementation. This is done on Proteus simulation. This is a very good method to test the values of components that you have chosen, and it gives you an estimate whether your system after networking, whether it will work or not, right? So this is what we had done. We tested our system for the given set of microprocessors, pins, devices, and contact points, the buttons and all installed. So this is a screenshot of it. Now we come to the design part, right? There were different parts of this entire project. So one by one, I'm trying to address each one of them as much as possible in details. Now this is done using Creo, right? So basically our aim was, if we tried to remodel the entire wheelchair, it would cost a lot of money, right? And we did not want to make it such a costly project, right? We wanted to ensure that free movement is there. Advantage of the material is available. The 3D printing can be done, right? The material should be flexible and not causing much friction to the body, because when a patient is on the wheelchair, the person is seated there for a long duration of time, right? So that with those concerns, we started taking those components which are mandatory to be designed and can be replaced in an existing wheelchair. We, however, did not replace all the components. The first part is the wheel. The calculation of the radius of this wheel is already shown in the beginning, last few slides back. Now, what happens is that if I make the wheels very light, the entire system may skid. The wheelchair may collide, right? So it was necessary to make sure that a balance is also available, because the patient may not be able to balance it on his own, right? So we opted for front wheels using this kind of design, and the back wheels, the rear wheels, we kept as it is. The regular wheels are sturdy enough, quite heavy. So there was a partial kind of modification introduced. The front wheels were substituted, the rear wheels were kept as it is. This way it ensured that sudden application of sudden brake does not cause too much of variation in the position of the wheelchair, but it takes care that within the house limit it will be able to cruise smoothly, right? There is one more point of contact that is often with the user, the patient of a wheelchair, and that is the handle. The handle where the person is placing his arm uh, is is in continuous contact, right? So that is the second component that we worked upon and tried to model it as per our requirement. Apart from that, the brake mechanism had to be taken care in the correct manner, because it is this brake which will be able to save the person whenever there are chances of collision, right? So these are few components that we worked upon, and we designed them as per the requirement of the special case, right? This may vary from person to person, and correspondingly the dimensions may differ, right? If you want to see the correct dimensions, they are available in the paper. This on the screen you can see two images. The one on the left hand side is the actual setup for the project, and this was placed just the detectors were placed on the front and the back side, right, of the seat, and the rest of the battery and setup was placed just below the seat, right? If you can make out, I had shown you a screenshot of this Android phone application before. At that time, there was no reading here. This 39 centimeter was not shown. So this is a screenshot when when the distance of the obstacle is at 39 centimeter and it is on the front side. We could also make out because we had used two sets of ultrasonic detectors, so the one on the front hand side, the other on the rear side. So this reading is corresponding to an obstacle that is present on the front end of the user, which is at a distance of 39 centimeter. We have just shown here one results, but of course we calculated it for many others. Okay, coming to the conclusion, a small torch on the left hand side, as I discussed somewhere during the entire presentation. The front wheels are designed using Creo 3. The rear wheels are kept same so as to ensure balance of the patient. Depending upon the household and domestic framework, the ultrasonic detector's height can be adjusted to avoid false detection. Now, false detection comes into the picture because ultrasonic detectors generally work in a straight line, and because your house may have a different configuration, so you can actually alter this position of the detectors, or maybe you can use some other detectors also if you think this will not work. The project is an attractive option, but our constraint was the batteries. The batteries are bulky. Hopefully, in future, if we get better batteries, we'll be able to perform better. Maybe someone else, if he or she takes up this task, will be able to give better performance than what we could manage to. We continued with this work, and we also published an IEEE paper, which is at Innovations in Power and Advanced Communication Computing Technologies, IPACT 2019, at VIT Vellore, India. What I have done at the end of the screen that is visible to you right now is I have shown you the link for this paper. It is on IEEE website. In case you have IEEE access, you can actually go there. In case you do not have IEEE access, you can go to ResearchGate, can search my name. You'll be getting this document because it is available. It is uploaded by me only. You can read through it. If you have any comments, if you believe you want to leave some suggestions, you can leave suggestions for me to follow back, or in case you are facing some queries in this respect and need support for working it out, then also you can leave the comments behind. Whatever you leave behind will be visible to me because the settings are done in that manner. Make sure your comments are motivating enough. These are the references that we have used in making this paper as well as the presentation both. So these are the 2 pages of references that we had available. The same references, most of these references are also available in the paper. So you can access either way, whatever is convenient to you. That brings me to an end of this session. Thank you. If you want to have some queries, we can now move on. So I'm stopping to share the screen.
Okay. Thank you, ma'am, for such a wonderful session.
Okay,
Thank you.
thank you. Thank you,
Thank you.
Ashwini.